Seeing is not believing. Our senses can deceive us. Even the stars are not what they appear to be. The cosmos, as revealed by science, is stranger than we ever could have imagined. Light and time and space and gravity conspire to create realities which lie beyond human experience. That's where we're headed. Come with me.
Back in 1802, on a night like this, the astronomer William Herschel strolled a beach on the English coast with his son John. Herschel was the first person ever to see into the deeper waters of the cosmic ocean. There, he glimpsed the magic trick that light does with time.
Father, do you believe in ghosts?
Why, yes, my son.
You do? I would not have thought so.
Oh, no, not in the human kind of ghost. No, not at all. But look up, my boy, and see a sky full of them.
The stars, Father? I do not follow.
Every star is a sun as big, as bright as our own. Just imagine how far away from us you'd have to move the sun to make it appear as small and faint as a star. The light from the stars travels very fast, faster than anything, but not infinitely fast. It takes time for their light to reach us. For the nearest ones, it takes years. For others, centuries. Some stars are so far away, it takes eons for their light to get to Earth. By the time the light from some stars get here, they are already dead. For those stars, we see only their ghosts. We see their light, but their bodies perished long, long ago. John, I have seen further back in time than any man before me, millions of years into the past.
William Herschel was the first person to understand that a telescope is a time machine. We cannot look out into space without seeing back in time. In 1 second, light travels 300,000 kilometers, or 186,000 miles. That's nearly the distance from Earth to the moon. So the moon is about 1 light second away. The next time you look at the moon, you'll be seeing 1 second into the past.
That sun? It's not really there. It won't actually be above the horizon for another 2 minutes. The sunrise is an illusion. Earth's atmosphere bends the incoming rays of sunlight like a lens or a glass of water. So we see the image of the sun projected above the horizon before the physical sun is actually there. That sun behind me is a mirage, no more real than the shimmering image that hovers in the distance over a desert road on a hot day. Sunlight takes about 8 minutes to reach Earth, so the sun is 8 light minutes away. From Earth, we can only ever see the sun as it was 8 minutes ago. And another thing, the sun doesn't really rise at all. The Earth turns, and we turn with it. It may not look like it, but right at this moment, I'm moving faster than a jet plane, and so are you and everyone on Earth. While I'm at it, that horizon, it's not really there at all. There's no edge. The horizon is just another illusion.
The distance between Earth and the outermost planet, Neptune, varies as the planets orbit the sun. On average, the light makes that trip in 4 hours. So for us on Earth, the Neptune we see is always 4 hours in the past, 4 light hours away. But the distances to the planets, even the farthest one, are mere baby steps on a much grander scale of the stars and galaxies. As soon as we leave the sun's immediate neighborhood, we need to change the unit of distance from light hours to light years. A light year is the yardstick of the cosmos. A single one is nearly 10 trillion kilometers, or about 6 trillion miles. It's a unit of distance just like a meter or a mile. It's the distance light travels in a year. The nearest star to the sun, Proxima Centauri, is a little more than 4 light years away from Earth. How far away is 4 light years? NASA's Voyager spacecraft moves at more than 56,000 kilometers an hour. Even at that astonishing speed, it would take Voyager more than 80,000 years to reach the nearest star. And the stars of the Pleiades cluster? 400 light years away. The ship of the imagination is equipped with a highly unusual capability, one of a kind, actually. It makes it possible for us to see what was happening when the light from a distant star or galaxy first set out on its long journey to Earth. When that light left the Pleiades about 400 years ago, Galileo was taking his first look through a telescope. A few years later, he tried to measure the speed of light, but he couldn't do it. He had a very clever plan, but the technology of that era just wasn't good enough to measure the motion of anything that moves as fast as light. When we look at the Crab Nebula from Earth, we're seeing much farther back in time. The Crab Nebula was once a giant star 10 times the mass of the sun, until it exploded in a supernova. At its heart is a pulsar, a collapsed star the size of a city, spinning 30 times a second. This pulsar's whirling magnetic field whips nearby electrons into a frenzy, accelerating them to almost the speed of light. They shine with a blue glow that lights up the tendrils of gas still unraveling from the supernova. The Crab Nebula is about 6,500 light years from Earth. According to some beliefs, that's the age of the whole universe. But if the universe were only 6,500 years old, how could we see the light from anything more distant than the Crab Nebula? We couldn't. There wouldn't have been enough time for the light to get to Earth from anywhere farther away than 6,500 light years in any direction. That's just enough time for light to travel through a tiny portion of our Milky Way galaxy. To believe in a universe as young as 6,000 or 7,000 years old is to extinguish the light from most of the galaxy, not to mention the light from all the 100 billion other galaxies in the observable universe. The center of our own galaxy is about 30,000 light years from Earth. The light we see today, coming from the core of the Milky Way, left there when our ancestors were perfecting a way to vanquish death. By making art with the power to inspire those who would come long after they were gone. The light we see coming from the Sombrero Galaxy is 30 million years old. Our ancestors were living in trees when that light started out. They weighed about 5 kilos and had long tails. But even 30 million light years away is still in our own cosmic backyard. That galaxy is part of the Coma Cluster, 320 million light years away. What was going on back home when the light you were seeing began its trip to Earth? No familiar continents, oceans, or rivers. Our distant ancestors were just leaving the water for the land. It's pretty old light, but not nearly the oldest light we can see. The oldest light is very faint, a pale ghost in the night. See that red blob inside the circle? That's one of the oldest galaxies we've ever seen. You're looking at 13.4 billion year old starlight, as captured by the Hubble Space Telescope. It's coming from the very first generation of stars. What was happening on Earth back then? Absolutely nothing. There was no Earth, no sun, no Milky Way. They would not come to be for billions of years. When we try to look even farther into the universe, we come to what appears to be the end of space. But actually, it's the beginning of time. Earth pulls on us. Our lives are a relentless struggle with gravity. That little girl is trying her best to climb out of a gravitational well. From our first efforts to stand to our final surrender, we are struggling to overcome the Earth's pull. We are born, live, and die in a force field, one that is almost as old as the universe itself. And how old is that? To visualize the 13.8 billion year age of the universe, we've compressed all of cosmic time into a single year-at-a-glance calendar. Midnight on December 31st is this very moment, right now. And January 1st is the beginning of time. See that glowing fog out there? It's radiation left over from the Big Bang, the explosion that made the universe 13.8 billion years ago. Right now, we're at the very edge of known space and time. So what happened before the Big Bang? Nobody knows. No evidence survives from before that moment. We've got some pretty crazy ideas about where the universe came from, which we'll get to in time. Where are we in the universe? At the very center. In the observed universe, everyone gets to feel special. No matter which galaxy you happen to live in, when you look out to the universe, you'll find yourself at the center of the cosmic horizon. But this is just an illusion. In reality, there is no center, and the cosmic horizon is no more real than the horizon at sea. It's what you get when you have a finite speed of light in a universe that had a beginning in time. A few 100 million years after the Big Bang, vast clouds of hydrogen and helium condensed into the first stars and galaxies. With these new sources of light, the long dark ages of the universe ended. As space continued to expand, cosmic evolution unfolded on grander scales. As the first generation of stars died, they seeded space with heavier elements, making possible the formation of planets and ultimately life.
Matter and energy were formed in the Big Bang. But that's not all. Space and time were created too, and all the forces that bind matter together, including gravity. Isaac Newton discovered a mathematical law that describes how gravity works. With that law, he could explain the motions of the planets. More than 100 years later, William Herschel realized gravity could do much more.
John, can you keep a secret?
Yes, Father.
I've made a discovery and have yet to tell another soul. The gravity that holds us to the Earth, the same gravity that Newton showed keeps the planets in their orbits, I've discovered that it also rules the distant stars.
Father, but how can you know this?
Can you find the constellation of the Lion?
There.
Well done. Can you now find the star that joins the lion's head to his body?
That one.
That star is really two stars, so close together that they appear to be one. I've been watching them through my telescope since long before you were born. They dance around each other very slowly, more slowly than any planet moves around the sun. Many of the stars we see tonight, perhaps most of them, dance with invisible partners. Gravity's empire governs all the heavens.
A century earlier, Isaac Newton had been haunted by the same absence of a mechanism for gravity. How could distant bodies affect each other across empty space without actually touching? This action at a distance, as he called it, baffled him. In the 19th century, Michael Faraday discovered that we were surrounded by invisible fields of force that explained how gravity works. The apple and the earth don't touch each other, but the fields between them do. He imagined those lines of gravitational force radiating out into space from every massive body. The Earth, the Moon, the Sun, everything. Here was the answer to that question that had stumped Newton. In 1865, James Clerk Maxwell translated Faraday's idea about fields of electricity and magnetism into mathematical laws. He discovered that these fields move through space in waves. When he calculated how fast they move, it turned out to be the speed of light. We were beginning to discover the threads of the cosmic tapestry, but we were not yet able to discern the rich pattern that time, light, space, and gravity weave. As Albert Einstein worked in Berlin on his theory of gravity, he kept the portraits of these three men before him. He knew he was standing on their shoulders. Years before, as a teenager, he had an insight that was as earth-shaking as any idea of theirs. And it happened one summer while he was daydreaming in Italy. In the summer of 1895,
Einstein's father's business in Germany had failed, and the family had moved here to northern Italy. Young Einstein loved wandering these roads and giving his mind free rein to explore. There's something timeless about this place. Nothing here has really changed since the time of Einstein's early daydreams. One day, he began to think about light and how fast it travels. In everyday life, we've always measured the speed of a moving object with respect to something else.
something that's presumably not moving. Something in the cosmos that's not in motion.
For example, I'm moving about 10 kilometers per hour relative to the ground. But as I mentioned earlier, the ground is moving,
Earth is turning at more than 1,600 kilometers per hour, while it orbits the sun at more than 100,000 kilometers per hour. And the sun is moving through the galaxy at 500,000 miles per hour. And the Milky Way is moving through the universe at nearly 1.5 million miles an hour. There is no fixed place in the cosmos. All of nature is in motion.
It was hard even for the young Einstein to imagine some absolute standard to measure all those relative motions against. This is the very book that inspired Einstein as a young boy. Give a kid a book, and you change the world. In a way, even the universe. Look at this, the very first page. It describes the astonishing speed of electricity through wires and light through space. Einstein remembered what he'd learned as a child from this book, and perhaps for the first time, right here, wondered what the world would look like if you could travel at the speed of light.
The more Einstein thought about it, the more troubled he became. If you imagine traveling at the speed of light, paradoxes seem to pop up everywhere. Einstein was shocked to realize that so much of what had been uncritically accepted as truth by even the greatest authorities on the subject was just plain wrong. When traveling at high speeds, there are certain rules which must be obeyed. Einstein called these rules the principles of relativity. Imagine that young woman who just blew past us on the motorbike. Imagine she was riding her bike through the cosmos. Light from a moving object travels at the same speed, no matter whether the object is at rest or in motion. Her speed is not added to the speed of light. The light from her motorbike still travels at the speed of light.
Nature commands, "Thou shalt not add my speed to the speed of light." Also, no material object can travel at or faster than the speed of light. There's nothing in physics that prevents you from traveling as close to the speed of light as you like. 99.9% of the speed of light is just fine. But no matter how hard you try, you never gain that last decimal point. For reality to be logically consistent, there must be a cosmic speed limit.
The crack of that whip is due to its tip moving faster than the speed of sound. It makes a shockwave, a mini sonic boom in the Italian countryside.
A thunderclap works the same way. So does the sound of a passing supersonic jet. So why is the speed of light any more a barrier than the speed of sound? The answer is not just that light travels about 1,000,000 times faster than sound. And it's not merely an engineering problem like building the first supersonic jet. Instead, the light barrier is a fundamental law of nature. Basic as gravity. Einstein found his absolute framework for the world, this sturdy pillar among all the relative motions within the motions of the cosmos. Light travels just as fast, no matter how fast or slow its source is moving. The speed of light is constant relative to everything else. Nothing can ever catch up with it. The thing about the laws of nature is that they're unbreakable. The job of physicists is to discover these commandments, the ones that do not vary culture to culture, time to time, and hold true throughout the cosmos.
That's why, as Einstein showed, funny things happen close to the speed of light. Traveling close to the speed of light is kind of an elixir of life, because your biological clock slows down relative to those you leave behind. This phenomenon may provide us humans, who only live for a century or so, a practical means to travel to the stars, where the magic show of space-time really gets crazy. The 19th century astronomer William Herschel loved to share the wonders of the universe with his son John.
I once had a friend, very clever fellow, an astronomer and a parson at Leeds by the name of John Mitchell. Poor man died when you were a babe, God rest his soul. He held that some stars are invisible. They really exist, but we shall never see them. Dark stars, Mitchell called them.
With all due respect, Father, surely your friend was mistaken. If no one can see them, then how can we possibly know they exist?
Did you see the man who left those footprints, John?
Why, no, Father. I did not.
But do you know that he exists?
John Mitchell is one of the greatest scientists you've probably never heard of. He lived and worked in England in the 18th century. If he ever sat for a portrait, it no longer exists. He was once described by an acquaintance as a short little man of black complexion and fat. Mitchell imagined a star so big, so massive, that nothing, not even light, could escape its gravitational grip. Can you find the dark star? Can't see with your eyes, not directly. But it may leave a kind of footprint on the cosmic shore. Mitchell realized that we might be able to detect some of these dark stars because of their extreme gravity. If one happened to be near a smaller, luminous companion star, that star would appear to travel in a tight orbit around nothing. Even though we can't see it, we know something with a lot of mass has to be right there. A dark star. Or what today we call a black hole. What does a black hole look like? And what would it be like inside? We'll get there. But first, let's make a pit stop in my hometown. New York City, where it's always seemed to me that everything is in constant motion.
I've lived here most of my life. There's always something new to see. One thing never changes: gravity. Gravity on Earth has been the same for the past 4.5 billion years. What if today we could alter it? Gravity is a distortion in the shape of space-time, as Einstein has showed. Space can expand, and contract, and warp without limit. If the Earth's size or density were even a little different, its gravity would be too. There's an infinite range of possibilities. New Yorkers feel right at home in the gravitational pull of the Earth, called 1G. Suppose we turn off the gravity on one of its streets.
People and objects that were already in motion are launched into flight.
Now what if I turn the gravity up to, say,
8 or 9 Gs.
out of compassion, let's evacuate the area.
This is about the same G-force that a fighter pilot in a high-speed turn would feel.
A few minutes of this wouldn't hurt you, but it wouldn't be comfortable.
At 100,000 Gs, even fire hydrants become crushed by their own enormous weight. But at millions of Gs, even light bows to gravity. The light still moves at its constant speed, but it cannot escape. Mitchell's dark star, our black hole. And the nearest one may be closer than you think. Not every star can become a black hole. Only about 1 in 1,000 is massive enough. The nearest one could be within 100 light years of Earth. Black holes aren't the mythic cosmic vacuum cleaners of science fiction. They don't go around gobbling up unsuspecting worlds. You've got to come to them. But if you do, it might be the last thing you ever see. That was us resisting a few million Gs of gravity. Don't forget, that thing swallows light. we'll keep our distance. When giant stars exhaust their nuclear fuel, they can no longer stay hot enough to fend off the inward pull of their own gravity. The most massive stars collapse into darkness, leaving only their gravity behind. This black hole enshrouds the shrunken corpse of a supergiant star. The star itself has shriveled into something even smaller than this darkness, only 64 kilometers wide. This is the first black hole ever discovered, Cygnus X1. How did we on Earth ever find something so small, and dark, and far away? We looked at it in another kind of light, X-rays. In X-ray light, we lost sight of the blue star because its surface is a tepid 30,000 degrees. But the disk of gas around the black hole glowed brilliantly in X-rays at 100 million degrees. As William Herschel discovered, many stars have close companions, forming a binary star system. But if one member of such a pair is enormous and the other is compact, the smaller star can drain and consume the atmosphere of its larger sibling. This neurotic relationship can last for millions of years. The atmosphere of the larger star was being siphoned onto a glowing hot accretion disk that revolves around and spirals into a black hole. The overwhelming gravity was accelerating the blue star's gas into a death spiral, crossing the space-time boundary, never to be seen again. The fateful boundary that separates a black hole from the rest of the universe is called an event horizon. From our point of view, the substance in the disk slows down as it approaches the event horizon, never quite reaching it. But if you were riding on that spiraling gas, and I don't advise it, you would sail past the event horizon in a matter of seconds into the undiscovered country from which no traveler returns. We have searched the hearts of dozens of galaxies, and in every case, we have found a supermassive black hole. Our own galaxy is no exception. The stars nearest the center of our galaxy whip around at more than 40 million kilometers an hour. What can make them move so fast? The only logical explanation is that something with a mass of 4 million suns lies at the center. So where's the blazing light of 4 million suns? Since we can't see it, it must be imprisoned inside a black hole. Earth is far enough away to be perfectly safe. Other worlds might not be so lucky. If you somehow survive the perilous journey across the event horizon, you'd be able to look back out and see the entire future history of the universe unfold before your eyes. How? Because when space-time is warped by the extreme gravity of a black hole, time is stretched to the limit. But what would be in front of you? Before we go there, I should warn you that we're entering uncharted scientific territory. For all we know, there may be undiscovered laws of physics that govern events at the center of the black hole. But until the next Einstein comes along, let's perform a thought experiment. That's how John Mitchell first imagined dark stars in the 18th century, and how Einstein conceived of his theory of relativity.
Do you believe in ghosts?
Oh, no, not in the human kind of ghost. No, not at all. But look up, my boy, and see a sky full of them.
If you could survive the trip into a black hole, you might emerge in another place and time in our own universe, circumventing the first commandment of relativity: thou shalt not travel faster than light. Nothing can move through space faster than light, but space is not mere emptiness. It has properties. It can stretch and shrink, it can be deformed. And when that happens, time is deformed too. Einstein discovered that space and time are just two aspects of the same thing: space-time. Space-time itself can deform enough to carry you anywhere at any speed. Black holes may very well be tunnels through the universe. On this intergalactic subway system, you could travel to the farthest reaches of space-time. Or you might arrive in someplace even more amazing. We might find ourselves in an altogether different universe. But how could a whole universe fit inside of a black hole, which is only a small part of our universe? It's another magic trick of space-time. The phenomenal gravity of a black hole can warp the space of an entire universe inside it. Our local gravity may be a drag to us, but it's really feeble compared with what goes on inside a collapsed star. As far as we know, when a giant star collapses, to make a black hole, the extreme density and pressure at the center mimic the Big Bang, which gave rise to our universe. And a universe inside a black hole might give rise to its own black holes, and those could lead to other universes. Maybe that's how our cosmos came to be.
For all we know, if you want to see what it's like inside a black hole, just look around you.
William Herschel went on to discover that the sun and its planets are moving through the Milky Way. And whatever became of his son, John? He grew up to become a great scientist. His deep space observations built on those of his father to become the basis for the standard catalog of galaxies we use today. When William was in failing health, John stayed with him through the long nights at his telescope to help him sweep the stars. And when his father died, John wrote his epitaph. He broke through the walls of heaven. John often reminisced about those summer nights with his father. Maybe that's why he sought a way to preserve the past. John Herschel was one of the founders of a new form of time travel, a means to capture light and memories. He actually coined a word for it: photography. When you think about it, photography is a form of time travel. This man is staring at us from across the centuries, a ghost preserved by light. It's not hard to imagine that in the near future, we'll be able to capture the past in all three dimensions. We'll be able to step inside a memory. It may not be possible to travel backward in time, but perhaps one day we can bring the past to us. Here's a moment from my past. Like John Herschel, I'm remembering a younger version of myself. December 20th, 1975. A snowy day in Ithaca, New York.
a branch point on the road that brought me to this moment with you. It was the day I met Carl Sagan.
Reminds me of those ghost stars in the sky. You know, the ones that still shine their light upon us long after they're gone.